Hello, in this lecture I'm going to do some examples for the linear elasticity problems with a constant strain triangle. Just two problems. I'm going to split the video in two. For the first part of the video, this first problem, which is it's actually not solving a linear elasticity problem, but just using the shape functions and derivatives of the shape functions to interpolate displacements and strains. So not really solving anything right now, but good warm up. And we have a mesh made out of two triangular elements. The coordinates are here in sort of the abacus format. So we have 0, 0, 2, 0, 2, 1, and 0, 1. And then the connectivity is given here. So first element is 1, 2, 4. So this element right here with the nodes number counterclockwise. And then the second element is 2, 3, 4. So again, sort of counterclockwise for the node numbering. And then we are given the displacement at all four nodes. So we are given all displacements. And what we're asked to do is to plot the displacement along the line y equals 0.5 and also plot the strain along the same line. So really all we need to do is just use the values of the displacements and interpolate inside of the element. And for that we need the shape functions, and I wrote this before because there's really not point in doing it during class, so you can look this up from previous slides, or I would give this to you, for example, if this was on an exam or something. We don't have any more exams, but yeah, I mean, you can just look this up. So the shape functions for the triangular element are like this. So they are linear shape functions on x and y, and they depend on the nodal coordinates. So what we're going to do is we're going to actually define the shape functions for element 1 and element 2. So for element 1, we have the coordinates of the element. So element 1 is this one right here. And then even though the global node numbers are 1, 2, and 4, the local node numbers are 1, 2, and 3. So those are local node numbers. So we have x1 equals 0, y1 equals 0, x2 equals 2, y2 equals 0, x3 equals 0, y3 equals 1. And with that we can write out the shape functions. So n1 of element 1, just plug in the values here. I guess in the area of the triangle is 1. So I'm going to skip the calculations because that's just by plugging in numbers. So this will be 1 over 2, and then 2 minus x minus 2y. Again, I'm just plugging in numbers into this equation right here. So you can do that and check that I did it correctly. For the second shape function, again, just plug in the values and you're gonna get 1/2 of x. And for the third shape function for element 1, again, just plug in the values, and this should say n3. And if you plug in the values, you'll get y. So that's for element 1. For element 2, which is this element right here, the global node numbers are 2, 3, 4, but the local node numbers are 1, 2, 3. And these local node numbers are given by this connectivity. So because I have here first node 2, then node 3, then node 4, that means that this is local node number 1, 2, and 3. And here I can have, based on those, the first point is the 2, 0 point, the second point is the 2, 1 point, and the third point is the 0, 1 point. And using those values, the area of this triangle is also 1. You can have the first shape function for element 2. Again, just plug in values here. And I'm gonna skip the calculations. So this will be 1/2 2 minus 2y. Second shape function, just plug in values here. And then you're gonna get 1/2 minus 2 plus x plus 2y. And then shape function 3 for element 2 is gonna be 1/2 2 minus x. Again, just plug in values. Alright, so now we have the shape functions for the element 1 and element 2, and we are going to need the derivatives. So I'm just gonna write them. Let me make a little bit of a separation here. So we need partial derivative of the first shape function with respect to x, and that's just gonna be minus 1/2. We are going to need the partial derivative of the first shape function with respect to y, and that's just going to be minus 1. Partial derivative of second shape function with respect to x, that's 1/2. Partial derivative of second shape function with respect to y equals 0. And then partial derivative of third shape function with respect to x equals 0. Partial derivative of third shape function of the first element with respect to y equals 1. And similarly here, you can calculate these derivatives. Again, just taking derivatives of these shape functions. That's it. Okay, so now I have shape functions and derivatives. So then I can actually interpolate the function, the displacement, inside of the triangle. So you can interpolate the displacement in element 1. So this will be u of 1, and that's going to be sum of the shape functions times the nodal values for the first element. So in this case, this will be n1 of 1 times the displacement of the first node, which we are told is 0, 0, plus second shape function of element 1 times the displacement at node 2. So this will be u at node 1, this will be u at node 2, plus the third shape function times the displacement at node 3, which is, I think, is 0.1 minus node 3 I should show. So in this case, for this element, actually probably should do it this way. So here we know u1, so local u1 is 0, 0. Local u2 is 0, 0. And local u3 is actually 0.1, 0.1. So note that that's not the same as the global node 3. So global node 3 is actually this one right here, but for element 1, local node 3 is global node 4. So that one has displacement 0.1, 0.1. So what we get is that the displacement for element 1 interpolated, it's going to be, so these are n1 and n2 are multiplied by 0, so actually it doesn't matter. And the shape function 3 is multiplied by 0.1, 0.1. Shape function 3 is y. It's this one right here. So actually the displacement for, and let me make the dependence explicitly. The displacement for element 1 in terms of xy is just going to be y times 0.1, 0.1. Or, 0.1y, 0.1y. So it's actually only a function of y. Let's do the same for the element 2. So interpolation of u2. For that, let me write out the displacements. So this one has local u1, 0, 0. So it's global node number 2, but local node number 1. This one has minus 0.1, 0.1, if I remember correctly. Yeah, so this one is global node 3, which has minus 0.1, 0.1. And then the last one is 0.1, 0.1. And that would be, so this is u2, and this is u3 of element 2. So in this case, the displacement for element 2 is going to be the first shape function of element 2 times 0, 0, plus the second shape function of element 2 times minus 0.1, 0.1, plus the third shape function of element 2 times 0.1, 0.1. So I can write it out explicitly in terms of x and y. So the first term obviously goes to 0, but the second term, so the second shape function is this one right here. So that one will be 1/2 minus 2 plus x plus 2y multiplying minus 0.1, 0.1, and then plus shape function 3, which is 1/2 2 minus x times 0.1, 0.1. You can probably simplify this a little bit, but you can see that this is a function of x and y. So I'm not going to simplify it. I'm going to leave it right at this point. So this one will be the displacement interpolated over element 1 is actually not a function of x, but it's a function of y. And the displacement over element 2 is this function of x and y. And then for the strains, what we want is the two different strains. If we want, I guess there's 3 different strains that we could calculate. So we can calculate the strain in x, which will be dux. I'm only gonna do one. So there's the normal strain in x, then there will be the normal strain in y, or the shear strain, which will be like this. So for the first one, partial derivative of ux with respect to x, that would just be the sum of the partial derivatives with respect to x times the ux values. So in this case, the partial derivatives of the shape functions with respect to x are, the first one is minus 1/2, but it multiplies 0. The second one is 1/2, but it also multiplies 0, so actually it doesn't matter. And the third one is 0. which multiplies 0.1, but it's 0. And then I'll just do one more. The second strain will be, so this will be EX over element 1, and then EY over element 1 is going to be partials with respect to y is -1, but it multiplies 0, and the second one is 0 and it multiplies 0, and the third one is 1 and it multiplies 0.1. So actually this gives you the strain in the y direction is 0.1 for element 1. And note that because this is a constant strain triangle, the displacements are functions of linear functions of x and y. In this case it's just a function of y, and the strains are constant. And you could do the same for element 2. And again, I'm not gonna do all of them to save some time, but for example, the normal strain for element 2 would be derivative of the first shape function with respect to x is 0 times 0 plus the second shape function is a half. Second derivative of the shape function is a half times minus 0.1 is the displacement in x of node 2, and the third one is -1/2 times 0.1. So actually the strain for this one would be -0.2 over 2. I will complete it for the before I upload to Blackboard, but hopefully you get the idea. So the main point is, in this case we were given the displacements at the 4 nodes, we were given the mesh, which consists of 2 elements, and then we are asked for actually displacements and strains along this line. So I still haven't evaluated along this line. I can still do that. But the main idea is that given the definition of the shape functions for the linear triangular element, which is directly in terms of x and y, you can just take out the nodal coordinates and get the actual expression for the shape functions and the derivatives of the shape functions, and then you can interpolate using those shape functions and the nodal values. And the key thing is that this has to be done per element, and you probably know this from what we have done in 1D and the work that we have already done for the heat transfer problem. So this is very similar to that work. If we want to interpolate the displacement, just sum of shape functions times displacements. In this case, as you can see, the first element has this displacement interpolation, the second element has this displacement interpolation. So here, for example, if you wanted to plot it along y equals 5, then all you will need to do is plug in y equals 5 here and y equals 5 here. And you'll see that what you will get is you will get a function. So in this case, if you plug in y equals 0.5, then you'll get that the displacement over the first element is actually constant along y equals 5. And here actually it's not. So here you will get some function of x for the second element. And then for the strains, just realize that the strains are just derivatives with respect to x or y, and then all you need to have is the derivatives of the shape functions and then times the nodal values. And I guess the only difference with respect to what we have done for the heat transfer problems is that now the shape functions multiply vectors, because now every node has a vector associated with it. So when we were doing the heat transfer problem, we had only scalar values per node. So here we have, for example, for node 1 we have a vector 0, 0. For node 2 we also have a vector, and for node 3 we also have a vector. So that's the main the main difference.